Oh, you got it? Thanks. Yeah, perfect. You might want to sit there if you're going to do it. Or he can go back. Oh, thanks. So if you want, guys, I can start rotating people through that. I'll just call name, and I guess I could add that to the daily quiz, right? You can pick camera work if you want. That sound good? Yeah, there we go. Sounds like a good tape every day. Well, yeah. Oh, also, I was thinking about it. Since I'm picking people at the start of class, another one of my customs will be if you come in late, I may just select your name. Otherwise, I have set up this system where I'm awarding you for coming 10 minutes late, right? You know, in some sense. Because in principle, here's what I was thinking. You could game the system. You just hold off until everyone else's name has been called. You're the only one left. You just systematically come late. Then you know you only have to study for that one day. You see, the whole point of this is I want you guys to be studying as we go so that, you know, you're up to date with things. Anyway, you can, we already hit record. I forgot. I will pray. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students and for this time we have together. I just pray that we would be able to use this time for your glory, Lord. In your name I pray. Amen. All right, let us discuss the problems. So A is 10, B is 2. We're given that the dot product of A and B is 15. Find theta between. So, yeah, we figured out theta was defined to be inverse cosine of A dot B over AB, which in this case is inverse cosine of 3/4, which is 41.40 degrees. I'm just going to trust that you did the calculator right. So, yay. No complaints. Over here, find the angle between this vector and the x, y, z coordinate axes. So this is, ooh, yeah, no. This hat is a hat you must wear. These are not optional. You got to put the x hat. X, y, and z we use for scalar variables, so we don't do that. Now, if you take another math course from me, x could be just about anything. It could be a matrix, it could be a vector, whatever. Like I use x in a very general sense, generally. But in here, x is pretty much a scalar variable. Similar comments. Hat, 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 hat. What do you think about that? I'm sorry, I just Dr. Seussified it. It's my bad. But yeah, these look right. So the inverse, the angle is the dot product of A dot x hat divided by that. The length of that is 1, length of that's 9. That dot product is 1. This dot product is 2. The dot product again over here is 2. So these look right to me. Very good. This one here, well, this is new, isn't it? But so how did you do it? You chose to do algebra, just plain old algebra, which is fine. So a plus b equals 3, a minus b equals 2, and then what did you do? You solved the second one for a and then plugged it into the first one. So that gave you 2b equals to 1. B is a half and a is 5/2. Very good, very good. Nothing wrong with this solution. Let me show you another one. So another way you could attack this would be to notice that if we look at 3, 2 dotted with v1, that will be equal to a v1 plus b v2 dotted with, I didn't expect you to do it this way, by the way. This dot, so this is equal to that, right? So I can take the dot product of the equation. Let's call this equation star, okay? So if we take the equation star and we take the dot product with v1 on both sides, we get this, right? But then by properties of dot products, this is a v1 dot v1 plus b v2 dot v1, right? And likewise, we can take the dot product of the equation with v2. Right, and by properties of the dot product, that's a v1 dot v2 plus b v2 dot v2. Right? Not an accident. He is wise. To watch the tape, John. Let's see here. So those dot products, if you allow me this short manga-style calculation. Oh, I'm sorry, manga. 32.v1 is what? It's 5. 32.v2 is what? 3 minus 2, it's 1. What is v1? What's v1.v1? I think I saw a 2. What's v2.v2? No, it's also 2. Sorry. Contrast of 2 and 2, hard to see. What's v1.v2? It is 0. Yes. And that is why this is actually a more friendly question than you realized, because all you have to do is take the dot product of that equation with v1 and v2 respectively, and it will immediately tell you that 5 is equal to 2a and 1 is equal to 2b. So therefore, a is equal to 5 halves, and b is equal to 1 half. Is that what we got? Oh, yay. Hey, algebra also works. You're like, I can go, I like the algebra. That's more familiar. But, you know, I want you to start thinking about dot products. Think about this. If I ask you the same question with 3 vectors, right, then all of a sudden you got to solve 3 equations and 3 unknowns with your approach. If I give you those vectors to be orthogonal, like these are orthogonal vectors, they're perpendicular, then you can use dot products to solve these kinds of equations sometimes. So this way of thinking is important. All right, now problem 4. So, you know, you win some, you lose some. And this is not quite right, because what we got to do is go, okay, so maybe invent a letter. Well, first of all, this is 110. So let's call that vector A, right? And then you can either take an algebraic approach and say, I'm going to just do it the natural way for me, which is a hat is 1 over root 2, 1, 0, 1, 1, 0. So then 7a hat is the vector I'm looking for. So you got 7 over root 2, 7 over root 2, 0. There you go. That's a vector of length 7 that points in that direction. I mean, alternatively, the other way you could do it would just be to solve this. You could say, well, I'm looking for x hat plus y hat times some constant, right? If I'm looking for that vector, let's call it a, with the length of a being equal to 7. That would be the direct algebraic approach. And if you work that out, that will force you to put c equal to 7 over the square root of 2. Sometimes students like to look at it that way. That's also fine. You can solve this. If we solve that, what is it? I mean, the length of a is what? The length of a is 7, and that would be equal to the length of c times the vector 1, 1, 0. Right? What is that? Yeah, so this is the absolute value of c times the square root of 2. Well, times the length of 1, 1, 0, which of course is the absolute value of c times the square root of 2. So apparently we can choose c equal to plus or minus 7 over root 2, right? So there are 2 answers, right? Oh, wait a minute. In the direction, I got to choose the plus, right? The minus gives me in the opposite direction, so I have to choose the plus. What's that?
Why did you multiply 1 over square root 2 to 0?
Because that's the unit vector. To find the unit vector of a, we take a and divide by the magnitude of a. Magnitude of a here, the length of a is square root of 2. This is a good question. And this problem we worked yesterday, right? So it's a little bit, I changed it up just ever so slightly. Yesterday I gave you 2 points, I mean, we looked at 2 points. We found a line connecting the 2 points, so I started the problem a little bit differently here. I gave you a parameterization of the line, all right? And so the line is the green thing. A point on that line, if we put t equals to 0, is 3, 4, 5. The direction vector, if you look at this, is 1, 1, 1. So it's called, so W, the thing we used, the thing that was W yesterday is played by the role of the direction vector in this solution. So W hat is 1 over root 3, 1, 1, 1, very good. And so if you look at this picture, we want to use the orthogonal let's put an arrow there. Orth goes that way. That's why we take 2, 2, 2 minus the orthogonal to get down to this point C, which is what we're after, the closest point to the line. And so we just have to calculate 2, 2, 2 minus, and this is the formula for the orthogonal projection. It's A minus the projection. Okay? All right. And then the rest is arithmetic, which I'm not going to do twice. So. All right. So I think we have talked a pretty good bit about the idea of a projection, angles between vectors, how to find vectors between points, you know. There are, of course, more things for you to learn. I will try to give you a more complete, well, actually give you a list of which problems I recommend. Hopefully tonight I will not just fall to sleep before I do that. I was apparently too tired last night to remember. Sorry about that. So any questions about the material here before I go on? So what I want to talk about next is the equation of a plane, and just sort of a little bit more about three-dimensional coordinate geometry. So let's talk about planes in 3 dimensions in R3. So let's just start the discussion by thinking of it geometrically, right? What's a plane? It's something like, ignore the width here, it's something like this, right? So we can sort of envision a plane, generically speaking, something like that, right? And I'm not sure where the x, y, z axis are. Let me just draw them as if they're here. I don't know really where they are. This is just kind of a picture. Here's x, here's y, here's z. I'm trying to describe this plane P, right? So to describe the plane geometrically, I really need kind of like 2 things, if you think about it. I need some point on the plane. Let's call that a base point. All right, so let's call that base point P naught. Right, I need some point on the plane. And the other thing I need is, once I pick a base point, right, I need to pick, so like think of the base point as being the middle of this perhaps. And I need to tell you what direction the normal goes, right? If I pick a base point and I tell you the direction which is perpendicular to the plane, that should describe the plane uniquely, right? So here's my rough picture of that, the normal. And we could use A, B, C. In fact, we kind of generally do that, A, B, C for the normal to the plane. All right. I'm talking to you as if you have some kind of already existing understanding of this word normal in terms of geometry. That may or may not be true. Don't worry, I will give you an algebraic definition very, very soon. So we'd like to describe, you know, if we take a point on this plane, let's say that point is, say, R, right? So this point P naught is, excuse me, if we draw the direction, we draw the vector from the origin, which gets to there, this guy, right? That would be the P naught vector, right? And where's the R vector in this picture? We could also envision it from the origin, right? Now, what if I draw the displacement vector which connects the base point P naught to the arbitrary point R on the plane? What is that in terms of vector addition or subtraction? I'll picture it right here. What's this vector? So this vector, ooh, sad marker. Oh well, I tried. Sometimes you win. Actually, that's not too bad. I shouldn't throw that out yet. This vector is what in terms of math? R minus P naught, right? Is what? Is what we would call is tangent to the plane. I'm using this funny looking P to label the plane P, okay? Right. N is the normal to the plane. Now, those are just words. Let's give them meaning. What's the relation between the tangent and the normal? They have to be perpendicular, right? If this is the tangent, the normal has to be like that, right? They have to be perpendicular. Getting back to my plane, if I have a vector which is tangent to the plane, like this one, screen. This is, if this vector on the plane is tangent, the normal has to be at a right angle. I need to get better. Gotta get better props. Actually, let's just focus on the prop which I can create, which is better, which is up here. So clearly R minus P naught, this should be perpendicular to the normal, right? So this is the vector equation for the plane P with base point P naught and normal N. And here R is an element of the plane. R is actually a point on the plane. Does all this make sense? I mean, it should be new, but does it seem reasonable? Okay, so this is great. This has its purpose, but we also like to think about things in terms of x, y, z. So what happens then if we give further detail here? So let's suppose that this point R is in fact x, y, z. So this is a variable point on the plane. We'd like to describe an equation for it. And this point P naught, let's suppose that that point is actually x naught, y naught, z naught. All right? So then what is R minus P naught in that case? So we're looking at x, y, z minus x naught, y naught, z naught, right? So that is actually just x minus x naught, y minus y naught, z minus z naught. And we're saying the equation, so if you look at R minus P naught, right, dot n, that is actually equal to x minus x naught, y minus y naught, z minus z naught, dotted with, well, n we said is ABC. What's that equal to? 0, right? So I mean, this right here, guys, this whole thing, this is really a definition. Here I'm defining what we mean by plane in Rn. Well, really R3, I suppose. There is a condition. What's the condition that we need on ABC? Suppose n was 0. What if n were 0? What R would solve this equation? If n was 0, which vectors dotted with 0 gives you 0? every single stupid vector. All right, so if you make n equal to 0, the solution set to this equation is all of 3 dimensions. That's not a plane, right? So you need the normal to be non-zero. At least one of the entries has to be non-zero. Not all of them, but at least one. And in that case, we take the dot product, and here we go. This is the standard equation for a plane that you'll see in most calculus books and so forth, and that we often use. Now, we don't have to go through this derivation every time, but I want you to understand the origin of this equation, and I hope I've done that for you. So that right there is the so-called scalar equation of a plane, or just the equation of a plane. Plane P with base point x naught, y naught, z naught, and normal A, B, C. Yes, sir.
Sorry, I think I missed something when you were writing the definition. It says vector is that EG to the C. What is that?
This?
No, the next thing. The first word, say vector.
Oh, that's equation.
Oh, that's all.
Yeah, this is my shorthand for equation. Hey, let's look at some examples. Yeah. If we have 3x minus 2y plus 7z equal to 12, right? Can you tell me a base point and a normal for this plane? How about this? If we rewrite this, we need to, this 12 we need to pick up over here somewhere, right? This is 3 times x minus 4, right? Minus 2y plus 7 z. Make my z more z, or script easy. So if you just pattern match, right? This, you can see, that's my A. This is B. This is C. And you can also see that x naught is 4, y naught, it's harder to see, but it's 0, and z naught is also 0. So we're looking at a plane with base point 4, 0, 0, and normal of what? 3 minus 2, 7. Yes, sir.
Where did the x minus 4 come from?
I moved the 12 to the other side. So minus 12 is, you know.
Okay. And you could have picked, could you have put that with the y if you wanted to?
Oh, there are infinitely many answers. Yeah. Because, I mean, is the choice of the base point unique? I mean, no, I can pick any point as the base point. So the base point's not unique. Is the normal unique? No, it's not. You can rescale it. You can make it longer, you can make it shorter, you could even turn the plane upside down, right? That would correspond to, you know, if I take this equation and I multiply by minus 2, what do I get? Minus 6 times x minus 4 minus 2 times plus 4 times y minus 14z equals to 0. So from this equation, you would see normal, you know, minus 6, 4, minus 14, and base point of still 4, 0, 0. This is really more my problem than your problem, because when I say find a base point and a normal for a plane, I have to be sensitive to this ambiguity in my grading. But you guys are creatures of habit, so you almost always solve it the way I showed you already. So I get the same answer from 25 people, and then 5 wrong answers. But no, everyone gets it right. Everyone gets it right. What am I saying? Any questions? Let's do another example. How about that? maybe even before we do that, it's worth noticing that what you could do here, another popular form of the line, plane rather, is just ax plus by plus cz equal to, d. There you can't see the base point. So what if you don't care about the base point? What if you just care about the normal? If you have the equation in this format, you can already see the normal, even though maybe you can't see the base point without work. Here, this d, what would it mean? It would be, in terms of the equation above, it would be ax naught plus by naught plus cz naught. It's all that stuff lumped in together into one constant, right? You could call this the, if I put a box around it, I think a good name for this would probably be the pointless equation of a plane. So, I gave you a pointless equation for the plane as a starting point for example 1. Just looking at this, I could tell you immediately normal is 3 minus 2, 7. Example 2, if I have 3x plus 2y equals to, 10, you've probably been conditioned to think that that's a line. It's a line through the origin. Oh, I'm sorry. It's a line, not through the origin. It's a line with, you can solve that for y, right? 5 minus 3 halves x, right? Well, that's lovely. But we're in 3 dimensions at the moment. Context matters. So that line, the y-intercept of 5 is over here, slope is minus 3 halves. I guess that means it looks something like this, right? I'll just focus on the part in the first octant. But that's true for which z? I'm looking at z equals 0 here. But does this equation say z is equal to, does this say z is equal to 0? It does not. It just says there's no condition on z. So geometrically, that means that you've got a stack of lines, which is a plane. So that's just the start of the story. You keep going up and up and up. I'm just drawing. It's infinite. It just goes on and on and on. What's its normal? It's 3, 2, 0, right? Which means that the normal is like parallel to the xy plane. Does that make sense? That it should be like that? So if I was so foolish as to attempt a picture, I better not. It's normal to that plane. I have trouble drawing too much at once, but. So what if I just want that line here? How would I get that in terms of equations? Let me make it green. If I just want this green line, and it goes on and on, how would I get that? Here's what I would do. I would want to say that 3x plus 2y equals to 10, and what else? Something else. Z equals 0. Yeah, you guys know it. You're good algebraic geometers. This is how algebraic geometry treats curves. It looks at curves as intersection, as the common solution to sets of polynomial equations. But you see that's kind of annoying, right? We need 2 equations in x, y, z to fix a line. That's why we've been using parameterization. Because parameterization, I just write r of t equals to whatever it is, we're good to go. How would you find a parameterization of that line? Can you tell me a point on the line? Here, how about, what's this point right here? Can you tell me what that point is? 3. Now, how did you know x was 3 there? Y is equal to 0 there. If y equals to 0, plug up in here, right? Yeah, x equals to 10/3. So the point is actually 10/3, 0, 0. So I could, if I wanted to parameterize that line, I could, for example, use the base point of that, 10/3, 0, 0. What would be a direction vector? What's that? Can you tell me a direction vector along that line? I mean, there are various ways to approach this. I mean, you could say, well, I'm going to figure out this point, right? That point. That would be where x is equal to 0. 0, 5, and 0. So what would this direction vector be then? See, we do minus 10/3, 5, and 0. There you go. That would be a parameterization of the green line. You want to gain a conceptual understanding of these ideas so that you can not just do the questions I've asked, you can do any question which is conceptually related to them. All right? I mean, yes, you want to solve problems that I've assigned you, but you should try to be gaining a conceptual understanding of these things so you can solve problems I haven't even said yet, you know? That's what your goal should be. You learn how to use these tools, you know? Like, I mean, I guess learn how to hammer nails perpendicularly, but don't be surprised if I ask you to hammer them in at 30 degrees off the, get used to how to hold the hammer. I don't know. All right, I digress. So there you go. In a nutshell, that's the equation of a plane. I mean, you can ask other questions like, are two planes parallel? What would it mean for two planes to be parallel? They have the same normal. Or the normals should at least be what? They should be scalar multiples of one another. I mean, it would be okay for, I would still say, if I had one plane with the normal 1, 1, 1, and I had another plane with a normal minus a million, minus a million, minus a million, those planes are parallel, right? So we actually don't have a sense of which is up and down when we talk about a plane in this sense, you know? Later in the course, we'll talk about oriented surfaces. In an oriented surface, you know which way is up, okay? And I guess you could talk about oriented planes, too. Oriented planes would say that the normal has to be on one side. And once you put it on one side, you have to stay on that one side for the normal. And a plane with the normal on the other side would be a different plane. I would say it would be a different oriented plane. All right, well. You can also talk about a parameterization of a plane, right? How would we parameterize a plane? If I have a plane like this, and if I have a point P, and if I have a point Q, and if I have another point R, and I wanted to find a parameterization of the plane containing the points P, Q, and R. So what should a parameterization look like? I mean, we parameterize a line with one parameter. How many parameters are we going to need to parameterize a plane? Well, not just one, right? Because there's a this way and there's a that way. I mean, there's two different directions. You already know that you need the x and the y parameters to parameterize the xy plane, right? So we're just generalizing that notion. If I decide that I'm going to use, let's say I'm going to use s and t for parameters, all right? And I'm just going to insist that we make P where we have s equals to 0 and t equals to 0. And I'm going to try to design some formula that makes Q be where s is equal to 1, but t is equal to 0. And I'm going to make R, I'm going to make that the point where, let's say, s is equal to 0, but t is equal to 1. So with that, here's a parameterization that'll work. R of s comma t. What I can do is I can just put the point P, all right? And then I do plus, I guess what I need then is I need direction vectors, don't I? Like, let me draw a picture of what I want. All my markers are askew. So this would be, let's say A. And let's say this guy up here would be B. So I'm insisting that A and B are tangent to the plane. They actually lie in the direction of the plane, all right, itself. Let's see here. So this point Q is actually what? It's actually equal to P plus A, right? What's the point R? R is actually equal to P plus B. So what formula should I write down to parameterize this plane? How about I do P plus S times A. Right, look, that'll work. When I put S equals to 1, I get P plus A. So S equals to 1 will give me the point Q like I want, provided whatever else I do is still 0. So how about this? Plus T times B. See how that works? Now, if I look at R, well, let me actually give you a slightly more pointed formula. P plus S times what is A? It's what? Q minus P, right? And that's T times what? R minus P. So this is the natural generalization of that 2-point formula I showed you to parameterize a line yesterday. This is the 3-point parameterization of a plane. Now that's only actually going to be an honest-to-goodness plane if these 3 points, P, Q, and R, are not collinear, right? If P, Q, and R lie in the same line, then we're not really talking about a plane here. Yeah. But anyway, there it is. So, all right. So, natural question that you want to ask, and this is, oh goodness gracious, I think if I go back and look at all of the Calculus 3 tests I've ever given, this is on probably almost every single first test, standard problem, and the problem is this. Given 3 points, P, Q, and R, they're usually, I mean, specific numerical points on the test. I mean, it's 1, 1, 1, it's 2, 3, 4, whatever. I mean, they're specific, but here's the generic statement of the problem. Given 3 points, P, Q, and R, find the equation of the plane P containing the given points. Right. Now here's the wrong way to solve this problem. What you could do is you could take those 3 points, right? You could put them over here into the parameterization of the plane. You could say, aha, well, a typical point on this plane is x, y, z. And then you would have, you know, you could set this equal to x, y, z, and then you could just work it out. You've got x equals to something, y equals to something, z equals to something. You have 5 variables, x, y, z, s, and t, and 3 equations, right? That means you can eliminate s and t and just leave yourself a an equation in x, y, and z, if you look at that carefully. But that, I mean, I've seen students get through it, but it's bad. That's not the way to do it. It's not the way to do it. So if we want to find a way to find the equation, this is not the equation of the plane, right? This is a parameterization of the plane. So let me just set up the problem. What we're looking for then, right? Here's my point P, here's my point Q, here's my point R. And again, I can think about, you know, this A vector and B vector like I was talking about, right? And I want to find the normal vector. I want to find a vector which is perpendicular to what? I want to find a vector which is perpendicular not just to the A vector, but also to the B vector. If I can do that, that gives me a normal to the plane, right? That's the problem, is how do you find a vector, right? How do you find n? This needs to be what? It needs to be perpendicular to both A and B. How do you find a vector which is perpendicular to a given pair of vectors? Right? If we could do that, then we'd have a way to solve this problem. And that is where the next product enters in, the cross product. The cross product is designed expressly for this purpose. The cross product takes two vectors, and it produces a third vector which is perpendicular to the given two. So here's the definition. And I have a nice lengthy motivation for this in the notes, which I would encourage you to read. And maybe I'll talk more about the motivation other day, but for today, we don't have time for that. I spent all my time showing you homework and test-like examples, which you probably, in the end, will appreciate that I did that. But anyway, here it is. A cross B, by definition, is AB minus AB, comma, AB minus AB, comma, AB minus AB, close. Now here, I'm not done yet. I'm going to use the notation. A is A1, A2, A3. B is B1, B2, B3. All right? And then the pattern is pretty neat. In the first component of the cross product, you just have 2 and 3 appearing in the indices. So you get 2, 3, and then 3, 2. In the second component, you have everything except for 2 appearing. You have 1 and 3 appearing. You have 3, 3, 1, and 1, 3. In the third component, you have everything except for 3 appearing. You have 1 and 2, and 1 and 2. This is the cross product. Yes, sir?
Wouldn't it be 2, 1, the last one?
Oh, yes. Thank you. Now, there are various ways to remember this. One popular mnemonic, and I have lots of talk about this in the notes, and I will use this sometimes, but x hat, y hat, z hat, and then you put A1, A2, A3, B1, B2, B3, and you take a formal determinant. Now, if you don't know what a determinant is, I don't see how this much helps you, but that actually means this. Let's try it out. So let's calculate, let's suppose, oh here, let's actually solve this problem while we're at it. What do you say? Let's make the point P the origin, so we don't go nuts. We'll make Q 1, 1, 0. We'll make R 0, 2, 3. Okay? So I want to calculate what's my, in this funny situation, that makes Q equal to A, doesn't it? And that makes R equal to B because P is the origin. Okay. All right, so I want to calculate A cross B for those vectors. 1, 1, 0, cross product with 0, 2, 3. All right. So let's see here. I do 2, 3. It gives me 3. And then 3, 2 gives me 0. And next I will do, the next thing I do 3, 1, which is 0, minus the 1, 3, which is minus 3. Enough with the double bars. I don't know if that really adds anything color coding wise. And then finally, the third component is based on 1, 2 minus 2, 1. So 1, 2, which is 2, minus the second component times the first component, which is 0. All right, so what do we got? We got 3 minus 3, 2. My question is that vector perpendicular to A and B? Check it out. This dot A is what? It's 3 minus 3 plus 0, 0. This dot that is minus 3 times 2, which is minus 6, plus 2 times 3, which is 6. Minus 6 plus 6, 0. So this is a simple thing that you can do to make sure you don't lose points. After you calculate a cross product, take 5 seconds to dot product your answer with the two inputs. If either of those is not 0, you are wrong, and you need to fix it. Okay? This is a simple thing you can do to not lose points here. All right? So don't be like the last Calculus 3 I taught and not listen to me about this. Like, actually listen and don't foolishly. I mean, this is a simple calculation. I mean, okay, it doesn't seem simple to you guys at the moment. I know it's new. It's got a lot of moving parts, right? But there's an easy way to check whether or not you're right. Other observations. The cross product is a vector, right? And versus the dot product, which is a scalar, right? To complete the thought here, so this tells me that we can use what for our equation to the plane? 3x minus 3y plus 2z equals to 0. Why did you might be like, what about the base point? What about the base point, right? Well, this plane has what on it? It's got the origin, right? So if the plane has the origin, then that d that I wrote, but I have since erased, that d is equal to 0. The equation for a plane through the origin is something like, ax plus by plus cz equals to 0. This is a plane through 0, 0, 0. Now, I'm not saying that other planes don't go through the origin. I'm just saying that that one definitely goes through the origin. Okay. When I have base points floating around, whether or not it goes through the origin can be kind of masked. That one definitely goes through the origin. Any questions? Yes?
So the 3x plus 3y plus 2z is the equation of the plane or the normal?
This is the equation of the plane that I was stating, this plane. It's the plane which contains the points p, q, and r.
Okay, and that's what
We don't write an equation for the normal. The normal is a vector, so we'd say this is the normal, I mean, I guess you could say that the equation for the normal, if you wanted to say that a cross b equals to n. I mean, if I was going to say an equation for the normal, I guess this is the equation for the normal, but I don't know. Anyway.
the plane is just the normal term of the equation. Or is that just a special case?
To understand the equation of the plane and its relation to the normal, we have to go back to the 15-minute talk I gave, motivating this picture and the normal, the relation between the base point and the variable point. All of those things led to the equation a times x minus x naught, b times y minus y naught, c times z minus z naught equals to 0. Any x, y, and z which solve that equation are on the plane P, which has normal ABC and base point x naught, y naught, z naught. If that's what you mean, then yes. Yeah. It's okay. Should do something else here. So let's talk about properties of the cross product. So I kind of led with an application. In past semesters, I have tended to just define the cross product, and I haven't talked about, if you go back and watch previous years of this, you'll see that I typically wait to talk about planes until after I've talked about cross products. But I thought about it, and I think it might be helpful to talk about it before. And so I changed things up a little bit. And you'll notice that in the notes. The notes go on and on and on about all this stuff we know about cross products. And then after that, I'm like, oh, here, plane, you know. Well, I don't know. Anyway, I'm not exactly following the precise order of the notes, but if you read the notes, it will help you. So properties of the cross product. First of all, A cross B is equal to minus B cross A. All right. That's a huge one. It also has the distributive property. If I have like C times B, I can pull the constant out. So you can pull scalars out of a cross product. It's pretty easy to see the fact that it's anti-commuting, that it's got that skew symmetric, that you get a minus from reversing the order. If you just look at the formula over here, see what happens if you interchange the role of A and B? It's like everything's the same, it's just the minus terms have become plus terms. So it's just, the proof of that's just directly from that formula, the definition. We also have additivity in the following sense. A cross B1 plus B2 is A cross B1 plus A cross B2. So it's distributive like that. So those are the basic properties. And we can already do an example with that. What's A cross A? Flip the order. What do you get? We get minus A cross A, right? Using this would be equal to A. So that tells us what? That tells us that twice A cross A is what? 0. So therefore, any vector crossed with itself is 0. Now is as good a time as any to contrast that with what happens with a dot product. You take A dot A. What do you get? You get the length of A squared, right? Furthermore, we've been working with this formula. A dot B is equal to AB cosine theta, right? So what's the magnitude? What's the biggest that A dot B can be? Well, that's what the Cauchy-Schwarz inequality told us. It said that that's less than or equal to AB. So if you think about it, the biggest that can be for when A and B are equal is A squared. So the dot product of a vector with itself is as big as it could possibly be. The cross product of a vector with itself is as small as it could possibly be. That's because the dot product is largest when the vectors are in the same direction, and the cross product is smallest when the vectors are in the same direction. So dot products directly measure sort of parallelness of vectors in some sense. That's why we're able to use them for projections. Whereas the cross product is all about perpendicular, right? Any vector is not perpendicular to itself. So if you ask what vector is perpendicular to a given vector and itself, the only reasonable answer you can give is 0. But, now you might wonder, well, okay, well this is a lovely formula. What's the analog of that formula for cross products? That actually requires a little work, and so it's going to take me some time to really prove this. And I think I should go through some of the details for you guys, not today, obviously, but we can prove a similar formula for the cross product. A cross B is actually equal to AB sine theta times n hat. that is, it takes some work to actually prove this formula, and I think I'll get into some of it in here tomorrow, most likely. But this is super useful because it also kind of tells you geometrically what the magnitude of the cross product means. If you look at A like this, and let's see here, A cross B. So if this is A, and this is B, and this is the angle between them, theta, what's AB sine theta equal to anyway? Let's look at this here. So this little right triangle, see that little right triangle there? What's the height? This is B, right? The hypotenuse is B. That's B sine theta. What's this length right down here? I mean, that's the magnitude of A is the length, right? What's the area of a parallelogram? It's the base times the height, right? So the significance of this factor right here is that the magnitude of the cross product is the area of the parallelogram with sides A and B vector. So that's kind of neat. Now you might ask, what on earth is n hat, right? That's where we got to get the right hand out. So you take, if this is A hat and this is B hat, take your right hand, you point your fingers in the direction of A hat, or A, right? And then you cross them. I mean, n hat is actually, this n hat is, well, I'm sorry, I'm kidding. I don't know, I put hats on A and B here, I'm an idiot. So suppose you got A and B. So A cross B, you point right hand in the direction of A, we cross the fingers into B, the thumb points in the direction of A cross B. So let's use a dot to indicate a vector pointing out of the board. Out of the board. If I reverse the roles, same picture basically, but I put A here, I put B here, right? So I have to point my right hand, direction of A, then I cross my fingers into the direction of B. It forces my thumb to point into the board. This is the right hand rule. So I just draw a little. So what we're thinking about is like an arrow. Oh, wait a minute. Yeah, these are the fins to the arrow. I got to remember the arrow. It's one of these like conical arrows, and then at the end of it, it's one of these deals. You know what I'm talking about? Any archers in here? This is kind of more like some kind of. I mean, I guess I shouldn't bring rockets up at the moment. It's kind of a sore topic. A cross B into the board. So geometrically, we need the right-hand rule to figure out which direction the cross product points. But anyway, my time is up for today. So I'll see you guys tomorrow.